Hello everyone. In this lecture, we are going to study and investigate fluid statics. So this is the second chapter of the book, the reference book. Uh, so in this lecture, I'm going to introduce and discuss Pascal's law and how the pressure varies in a fluid which is at rest, okay, for a fluid at rest. And then after that, we will talk about incompressible fluid, and we will solve some examples for this, for finding the pressure in a fluid at rest. So before moving forward, because the arguments that I'm going to make to find the pressure in a fluid for a fluid element or fluid element needs some background in Taylor series, because we are gonna talk about derivatives, and you're gonna take derivatives around the point, and so you need to have some background in Taylor series, and you need to refresh your previous courses, especially calculus by Taylor series, because we are going to use this concept a lot in this course, especially for proving some basic theories and fundamental theories for the course. And of course, when you have the formula, you can apply it into different examples, but just in order to drive those formulas, we are going to use Taylor series. So here I'm going to give you a brief overview of Taylor series for those who have might forgotten that. So this is something that is not in the book, but I'm just giving you this overview, or especially for people who might have forgotten this. So a reminder from calculus. So what is Taylor series? So Taylor series is a representation of a function as an infinite sum of terms that include functions derivatives. Okay. So, for example, say we have a function like this. Any function is a very general theory for that is true and valid for any type of function. So assume or suppose we have this arbitrary function here, something like this. Okay. And now what I want to do is, I know I want so let me just write it here. This is fx, a function. So this is f, and this is, so let me just write it. This is f and this is x. So here I have this point, say A. Okay. And the question is, how can I approximate f around x equals to A, right? So the question we have is, how can we approximate f, function f, around x equals to a. So, and in order to do that, we can use all the different derivatives. So let's say, just in a close vicinity or close vicinity of this function, somewhere around here, I want to approximate this f based on the value of f at here, at a, and any derivatives around a. So I want to approximate here, say, based on the value of f at a, which is this green one, plus any derivatives, like first derivative, second derivative, or third derivative of that. So how am I gonna supposed to do that? So if you look at it, if you are in a close proximity or vicinity of that to a first order, you can say that you can approximate this function with the first derivative, right? So if I plot the first derivative at a, this is the slope or the derivative, first derivative, which is just going to be the slope of this function at that point. It's not necessary at 0, so let me change that a little bit so you are not confused. This is not necessarily, it shouldn't necessarily become cross 0 point. So let's make it very general. So the slope of the line here okay, I think this is good. So you see, if this kind of proximity is kind of close, then if you add fa to its to first derivative, you are going to get somewhere around here, right? So you have a pretty good approximation of the value of function around it, correct? The same thing for this here, right? So if you add it, you are going to get this point, which is kind of close to this point, right? So they are kind of close to each other. So the whole idea of Taylor series is this, that you add all the derivatives to get the very exact approximation around x equals to a. You can use all the derivatives, okay? So let's see. I'm gonna formalize this. So I'm gonna say qx is the value of function f at point A, so this is fa, right? Plus the first derivative at point A, which is f prime A, times x to the x minus a. Okay, so this is f prime A times x minus a. So this can be x minus a. It can be any point, right? plus other derivatives. So I'm going to just write it as c and then try to find c. X minus a square. Okay. So what do we require? We require first QA, if this is the approximation for f, right? So this is approximation for f around x equals to a. So first we want and require QA should equal to FA, right? So this is the first requirement. We want the approximation to be exact at point A. And if you look at here, that's why I use this term, because if I were to use something like cx squared, then this term would become 0, but then I would have another term here, right, which is ca squared. So then this requirement was not valid. So that's why I use c times x minus a times square. And then you can have also other terms like d x minus a cube. For all of these, at x equals to a, qx is going to be qa equals to fa, right? Because x minus a at x equals to a is going to be 0, and this term is going to be also 0. So qa equals to fa. Okay, so this requirement is already satisfied because of the choice that I made for the coefficients x minus a and x minus a squared. And to make this approximation even more accurate, I also want this approximated function, its derivative, first derivative, second derivative, I want them to be also equal to the derivatives of the fx function. So the second requirement that I'm going to make is q prime at a should equal to f prime at a. Okay, so let's investigate this. What is q prime? So q prime is going to be q prime x. Let me write it here. Q prime x is the first derivative of q with respect to x. So fa is a constant, so it's going to be 0, the derivative with respect to x. The second function, I have the coefficient, which is a constant f prime a, times x minus a. So it's going to be 1 minus 0, right? The derivative of a is constant, so it's going to be 0, and x is going to be 1, plus the second term is going to be c times the derivative of the second function is going to be x minus a times 1, right? So this is the derivative of this function with respect to x. And again, these are all from your calculus. So let's see what we are going to get. So we are going to get q prime at x equals to a. Let's see, q prime a, which is what we have here, and I want to have it, equals to q prime at x equals to a, and q prime, I have it here, q prime x. So I'm just gonna put f prime a, x equals to a. So I'm gonna have 2c a minus a. Instead of x, I just put a. So this is gonna be 0, and thus q prime a equals to f prime a. So again, because of this choice that I had, this because of the choice of x minus a squared, this requirement is also satisfied. So the first derivative of the approximation function for f is also equal to the first derivative of f at point A. So now I'm going further and further. So I want to also the second derivative of A of Q at point A to equal the second derivative of f at A. So let's see what does this ensue. So we are going to get q prime, we had q prime x. So I want now to get the second derivative, so q double prime x. So I have it here. So it's going to be the first term here, this one is all constant, right? F prime A is constant, 1 minus A is constant with respect to x. So this is just going to be 0, the second derivative. So I have 0 plus the second term is going to be 2c times x minus a, the derivative of x minus a. So the derivative of x with respect to x is 1, and then the second one is 0. So this is going to give me 2c. Okay. So the derivative of x q at a point A is going to be 2c, and I want it to be equal to f double prime A. So from here, in order for this requirement to be satisfied, c, which is the coefficient we defined here, has to equal f double prime A over 2. So if c equals to f double prime at point A over 2, then this requirement is going to be also satisfied. So q double prime A is going to equal to f double prime A. Okay. So now I want to give you small exercise at home that you can do it. And that is, so for qx, you just add the third term. So we have qx equals to fa from here, fa plus f prime a, x minus a, plus, and we found this c, which is f double prime a over 2 x minus a square. I want you to add the 1, 2, 3rd, 4th term as d x minus a cube as an exercise for yourself. And then investigate all these requirements, and in addition to those, also try to satisfy this one, which is q triple prime at A equals to f triple prime at A, and then find what d should we have in order to satisfy this requirement. What should be the value of d? So essentially you need to do the same thing, right? So you need to take another derivative, but by adding this d term as well into the expressions here. Okay. So if we keep doing this, so this is exercise at home. And I'm gonna write the general form of that here. So you can pause here and solve this, but I'm gonna write the general form of this, that what is the trend, because if you write this, find D and then add the other term like EF, further terms, you will find a trend. And that trend is what we call Taylor series. So if we require higher order derivatives of the approximation Qx to be equal to fx derivatives we get Taylor series expansion. Okay. So I'm going to write the general form of that. Instead of qx, which is an approximate function, I'm going to write fx. And the reason for that is if you keep doing all of these derivatives until infinity, you can prove that this qx is going to equal to fx. And the reason is why? Because you are actually making sure that all the derivatives of the approximation function qx equals to all the derivatives of fx. So the only way that these two can equal to each other is that qx equals to fx. So qx has to be exactly fx in order for it to all of the derivatives of that equal to fx. Okay, so I can write the Taylor series expansion fx can be approximated around point A as the value of f at point A plus f prime, the first derivative of A, times x minus A, which is what we have here, plus the third term that we found from here, the C, is going to be f double prime A over 2 x minus A square. And then the third term, I'm going to write it as factorial because this is going to be the trend, is f3 or f triple prime of 3a over 3 factorial x minus a cube and plus other terms. The same trend that you have here, right? So this is kind of the answer to this question that I asked. So this is going to be your D here. And I want you to drive it based on this argument that I made. Okay, so this is going to be the solution of that, just in case. So f3 is just f triple prime, right? We can just write it as f3 as well. So this is just a nomenclature. Okay, so this is very important. This is very important. result that we got is very useful, and we are going to use it for driving the pressure. And we are in also other parts of the course, we will need this Taylor series expansion, because this is very useful for approximating especially elements near some surfaces. Okay, so this is the approximation of f. We can write it as based on the derivatives at point A according to this formula. Okay, so this was the proof, and now I just want to, and also introducing the Taylor series expansion. So just a quick example. Write the Taylor series expansion, or the Taylor series for ln, which is logarithm, natural logarithm of x at x equals to a. Okay, so I'm gonna do this for you so you better understand how you should do this. So fx, the Taylor series, is gonna be, my function is ln x, which is gonna be, I can write it at around point A as fa, which is the first term here, so I'm just gonna write it down. So it's gonna be ln a, logarithm of a, plus the second term is f prime x at point A. So what is the derivative of ln with respect to x? Try to recall it from your calculus. It's gonna be 1x, right? And because it is at point A, I'm just gonna write it as 1 over a times the second term is gonna be x minus a, which I just write it down here. And then the third term is gonna be the f double prime x. So let me write it down here. F prime x is gonna be 1 over x. F double prime x is gonna be the derivative of this function with respect to x. So this is what? This is just x to the power minus 1. So it's gonna be minus 1 times x to power minus 1, which is gonna be minus 2, right? So it's gonna be minus 1 over x squared. So here I'm gonna write minus 1 over x squared, which is going to be a squared, times 2 factorial, which is what I have here, times x minus a squared. Okay? And then so on and so forth. So you just continue this series, and this will be the Taylor series for ln x. So ln a plus 1 over a x minus a minus 1 over a squared times 2 factorial over times x minus a squared, and so on and so forth. So this is another representation of ln x. Okay? And you can do it for other functions like sine x. And I ask you to do this for your at home. I'm just gonna do the first terms, and I asked you to do the other terms. So it's gonna be sine a plus the first derivative with respect to x is gonna be what? Is gonna be cosine x. So I have cosine a, all right, times x minus a. And then second derivative, so cosine x is going to be minus sine x, so I have minus sine a over 2 factorial times x minus a square, and then you do other terms. Okay. So you can do it for any function. For any function, you can write the Taylor series based on this formula that is shown here, and this is a very important formula that we are going to use. Okay. So now I want to use this Taylor series to drive some important phenomena in fluid, which is understanding and characterizing the pressure variation in a fluid from point to point. Okay. So let me start here. First, let me define pressure. What is pressure? So pressure is, if you remember the first lecture, it is normal force per unit area, right? So the force, for example, over something with a normal force, right? Not the shear force, okay? A normal force per unit area. If you have area here, we just you just divide that, and then you will get the pressure. So, for example, over this, you have this area, and then you have this force, normal force. So pressure is going to be F over A, unit area. Acting on a given point. So this is also important, acting on a given point. This is going to be the pressure at that point. Okay? So this is the definition of pressure. And now I want to discuss a general law in fluids, which is known as Pascal's Law. So Pascal's Law states that the pressure at a point in a fluid is independent of direction as long as there are no shearing stresses. So as long as there is no, or there are no shearing stresses, then the pressure at the point in a fluid is going to be independent of direction. This is the Pascal's law. So it doesn't matter, for example, if you have water, a tank of water, and then you want to know what is the pressure here at this point. If there is no shear stress, like for example, it is at rest, the fluid is at rest, then the pressure here is going to equal to the pressure here to here to here. The pressure is not a function of direction. we are going to have the same pressure at any point in a fluid. Okay, and this is known as Pascal's law. Okay, so now I want to use this and then answer a question, and that is, how does the pressure in a fluid vary from point to point? So the question I have is, how does the pressure in a fluid vary from point to point? Okay, so I'm gonna answer this question after the break. So let me just review what we did today so far. So we started with the Taylor series. Just a reminder from calculus, that is a representation of a function as an infinite sum of terms that include functions derivatives, right? And then we started with this question, how can we approximate f, this any function, as around x equals to a. So we introduced this approximation function and we tried to satisfy all these requirements, which is q at a, the approximated function, the value of that function at a should equal to the value of f at a. The first derivative of them should be equal, the second derivative of them should be equal, and so on and so forth. And then using that, we got this series here. And then for higher order terms, we say if we also require all the higher order derivatives of this approximation function to be equal to fx derivatives, we finally get the Taylor series expansion, which is this expansion in a general form. And then we did some examples for Taylor series, for example, for two functions, for logarithm, the natural logarithm of x and also sine x. And then we define the pressure, normal force, unit area acting on a given point in a fluid. And then talking finally about the pressure, the Pascal's law, which the pressure at a point in a fluid is independent of direction as long as there are no shearing stresses. So this is the general law. And finally, we are going to use this law and also this Taylor series to find the pressure variation in a fluid from point to point.